Hi everyone, and welcome back to the Generative AI class. And so, what we will do today is that we will kind of build on what we learned about GANs and move to a more powerful version called the conditional GANs that I was um, introducing last time in the previous video. You can check. So in the regular or vanilla GAN, the idea is that we are going to generate kind of purely from random noise some data. That data is going to look or it is similar to real data, yes, but what I can tell you is that we have no control over that data. It's like I mentioned before, I cannot force my GAN to generate the image with this or that conditions, or I mentioned this or that characteristics. No, not at all. If I am, and in our labs, we mainly use the MNIST dataset. And so if I have my data set and I want my GAN to generate some images, if I am going to use the NNIST data set, which is the data set containing 70K images of handwritten digits from 0 to 9. And if the generator is going to generate some fake data, which are the numbers that look like our real data, let's say, but it can generate number 0, it can generate 1, it can generate 3, it can generate 9. There is no control. It's not like I can force the generator and I say, now please, you are going to generate for me number 4. And this particular or specific, given this particular or specific label, the generator is going to give me the corresponding images. So this is not happening in the typical GANs. However, this is possible in the conditional GANs or the cGANs, like I told you last time. Okay, so let's try to get a quick reminder about how GANs work first. So we previously mentioned that GAN has mainly, let's say, two parts. The generator that is trying to produce fake data that look like real data, and the discriminator that tries to distinguish, let's say, between the real data, or it's going to distinguish exactly the real data from the fake data. So they compete like cat and mouse game, okay? And the generator, in this case, improves because it wants to fool the discriminator. The discriminator, in the other hand, it improves because it wants to catch the generator. And this is mainly the interaction that is guided by binary cross entropy loss, okay? So why we need conditioning. So okay, it's useful from the example I given, but the issue with GANs, like I mentioned, that we cannot control the class of the generated samples. Like we want this ability. We want to say generate a 1, generate a 4, or generate a 9. We want to do that. So to achieve this, we provide the model with conditioning signal. It's like an extra information that tells to the model that what we want the model to generate. Okay, so what class I would say conditioning works, let's say for our case, and like I mentioned, we use the MNIST dataset. Okay, so in MNIST, each image comes with a label from 0 to 9, right? Because we have 10 digits. So during the generation, we still sample the usual random noise. That step is still there. We sample the random noise, but what we do is that we also sample kind of random labels. So you see here fake labels. So, and let's say I can say, for example, digit 3, digit 4, digit 5. Okay, these are random labels. Okay, and we feed both the noise and the label to the generator. So the generator that usually takes only some noise, generate images. Now we are going to feed it some fake labels. Okay, and what will happen next? The generator must now create an image that matches that label. Okay, and it's like the fake data. Okay, then for training the discriminator, now what will happen? we pass, like we used to do before, the real data, I would say, the real images and the real labels, but also we give the fake data. And in this case, the fake data, which is mainly conditioned on fake labels, right? So you give it the fake like images plus the same labels that you are mainly using them for, I would say, generating that like fake data. Okay, so now the discriminator must learn to classify real vs fake. Okay, and the idea is that given the label information, we are going to do this. This is new in this case. So the discriminator is no longer, I would say, checking real or fake alone. It checks also real or fake given this label. Okay, so given this label, is it like real or fake? Okay, so this is mainly the key idea behind conditional GANs. So how we embed the label now? We do that like I was showing you in here, and there are different ways also to include that conditioning information in terms of coding. Now it could be by adding it. Okay, it could be by concatenating it, and later, or maybe in some advanced models, it could be by using what we call cross attention. Okay, so today what we will do is that we are going to use the concatenation approach, let's say, which is straightforward and that works well with the MNIST data. Okay, so we can now condition again in several ways by adding the label information. I would say concatenating it, embedding it. You just like try to learn these three. Okay, and in our lab we are going to use the most simple, like I was mentioning it. The way it's going to work is mainly that for our case in the lab 3, what will happen is that we're going to convert the label into one hot vectors. We are going to concatenate the label with the noise for the generator, and we also concatenate the label as additional channel to the image for the discriminator. Okay, so this is mainly the idea. And in order to summarize before moving now to the lab, I just want to tell you that the idea is simple. It's kind of like we have a regular GAN that generates anything. This is there, but what happens in a conditional GAN is that we're going to generate, but giving the condition, like what you ask it to do. This is what we would do. It's not going to generate random, I would say, images. It's going to generate what you ask it to generate. Okay, so we give the generator a label, and it produces an image that matches that label. And what also we do is that we give both generator and discriminator the label. So the discriminator learns to check whether the generated image matches the required class or not, and this gives us a full control over the generation process. Okay, so this is mainly the idea that we are going to implement in lab 3. So like always, so you have the link to the lab, and here is it. So lab 3, I know that my main objective in this class is that you guys learn. So mainly I want you to learn, and even that I'm guiding you, it's your opportunity to learn. Okay, so for this lab, the idea is that we're going to go through the lab together, because I was thinking to give you this lab as an assignment, and based on the information and things that we learned through the presentation, you're going to explore the lab by yourself, but I thought it's not a good idea. So mainly this lab, it's like we are working on it together. Okay, so you are going to open your laptop, you are going to open the link for lab 3, and you are going to go through each and every cell, but you're not going to do that alone. So I will be with you. Okay, so it will be a teamwork. I will be with you, and we're going to explore these conditional GANs. It's like the idea that we're going to train a GAN conditioned on a class labels, to generate 100 digits like I previously mentioned. Okay, so let's go quickly through some readings. I will not read a lot, but I will read the most important parts. Like generative adversarial networks, GANs, let us generate novel image data, video data, or audio data from random input. So it's true that in the slides, I only focus on image data, but still these powerful techniques, they allow you even to work with videos or audio, and you can even explore that by yourself if you want. Okay, so it's not part of this class for now. We are mainly focused on image data. Okay, typically, like the random input is sampled from a normal distribution before going through a series of transformation that turns it into something like plausible, like image, video, or audio, and so on. In our lectures, we focus with the normal distribution. Now we are familiar with normal distribution. We understand the theory behind normal distributions, and I did my best to train you really well and give you all the foundation. So if you are exploring a lab like this, for example, you don't feel like, what does this mean or what is this? Okay, so however, a simple DC GAN, and I was mentioning the paper for this. So one of the papers, like I was giving you, that I say you can work with that as your project, is this very famous paper, okay, unsupervised representation learning with deep convolutional generative adversarial networks. So this is mainly the basic architecture that we covered in this during the previous video, I would say, or recording. So this does not let us control, I would say, appearance, which means like it's a vanilla GAN, and you cannot force to give you number 9 or number 3. You cannot give it the class that you force the generator to generate images with respect to that. Okay, so for instance, with a GAN that generates MNIST digits, a simple DB would let you choose the class of digit we are generating. This is what I was just explaining. So what to do is to be able to control what we generate. We need a condition, the GAN. So this is the cGAN or conditional GAN, and it outputs in this case a semantic input such as the class of an image. Okay, so for example, what we will do in this class, we are going to build this. Okay, so and it's going to generate like MNIST handwritten. Okay, so let's just move. Okay. Here I was supposed to start with the imports, but just to avoid some errors related to this import of docs.vis, so I just did this pip install because I had that error there. Once it's done, we can just go and run the next cell, which is mainly about the importing the libraries. Okay, so mainly we need keras, layers, ops, embed, TensorFlow, embed, and TF, it means TensorFlow. We are going to use an NumPy as MP and image IO. Okay, so these are mainly the imports that we have. It's running the cell, there are no errors, and everything is perfect. Now let's define few, I would say, parameters or few variables, sorry. So we're going to define the batch size equal to 764. The number of classes, num channels, sorry, of channels is equal to 1. Num classes, number of classes is equal to 10. The image size for MNIST, we know that is 28 by 28, so 28. The latent dimension here, we choose it to be 128. Note that, so we can play with these hyperparameters, but maybe some things we cannot change, like the image size or the number of classes is something fixed. Okay, channel this class equal to 1 also. So let's load MNIST now data and pre-process it. So in this lab, nothing is different from previous two labs. Lab 1 and lab 2, we already did the same thing. So you guys were I would say uploading the MNIST data set, and you were like using the already available data set, you loaded it from keras.datasets.mnist. When you do that, so mainly you have your training data and your test data. You have two sub-data sets. And as the data set is 70K, so it contains 70K samples. So the train data is kind of a 60K images and the test data is 10K. And next, what you have here, you have all digits. You are going just to concatenate X train and X tests. There is no here differentiation between train and test. So you are concatenating, you're having a total of 70K images. Or labels, so you're having a 70K images for both train and test labels, I would say. Then what you will do, you are kind of scaling the pixel values to be between 0 and 1. It's a normalization step. Okay, and you add a channel dimension to the images and one hot encoding labels. Okay, so don't think that it's a boring lab and just going through it because I don't want to assign you go through it by yourself. Otherwise, it's really well detailed, well commented, and so the idea is that we just need to go through things and we explore and understand. This is my main objectives, or this is what my main goal from this lab. Okay, so here what we have, we're just going through this normalization, and we are reshaping our data. We are preparing data for the model for the training step. Okay, and next we are creating like TF data set. So the idea is that we are using it from tensor slices. Okay, so at the end, what we wanted is that we don't want train and data separate. We want the whole data together for images and then the whole label, I would say, together. So what we have in here is finally, after the pre-processing, our training images with their content pixel values, they are between 0 and 1, normalized and all. So we have 70K images. Each of them is having 28 by 28 dimension, and it's like one channel we are considering. For the labels, we have 70K labels, and they hold values, distinct values. If we count them, they end up 10 values because we have 10 classes from 0 to 9 for each of these 70K images, okay, grayscale images. Now, let's start. First step is calculating the number of input channel for the generator and discriminator. So in the regular like GANs, we are not in the case of conditional GANs. We start by sampling noise. In this case, like for, let's say, a given some fixed dimension for like, for example, from a normal distribution, like we always did. In our case, we also need to account for the class labels. We will have to add the number of classes to the input channels of the generator, which is the noise input, as well as the discriminator generated image input. Okay, so in terms of code, we have the generated in channels. It's the latent dim plus number of classes, which are 10, and this is equal to 128 and 10, which is, we sum them together, we find the generated class, if we print, is the sum of 128 plus 10. It's 138, exactly what we see here. So I didn't run this cell, but it's supposed to give the same result. Yep. And next we see the discriminator in channel, which is the like 11, coming from the sum of number of channels that we have only one, and the number of classes, which is equal to 10. So 10 plus 1 is equal to 11. This is what we are just checking before moving on. So creating the discriminator now and generator. The idea is that if you remember in the previous video, we had that pseudocode that I given you for the vanilla with cGAN. And so these are the steps that we are implementing. I say like the puzzle, the pieces of the puzzle, and this is what we are doing here. So as you can see, for creating the discriminator, it's a sequential model. So you start, it's a discriminator equal keras.sequential. And then the sequential model starts here and finishes here. It contains different layers. So we have mainly the input layer, okay, size of the image 28 by 28, and the discriminator in channel equal to 11 here, okay, the sum that we are computing so far, right? So next you have the convolutional layer. we are giving here like these dimensions and these like these filters and these kernels, this the stride and the padding. So these are the parameter of the convolutional layer that we are just giving. So or next after each convolution there is here the likely reuse, or you're just giving the number the like negative slope point two. Then we have a global max pooling layer and a dense layer, only one like neuron. So this is mainly for all for the discriminator, just calling it discriminator. So later when you see discriminator, it means this part, okay? Next, now for the generator, we say that it's kind of the opposite. So we have the dense layers, okay? Then we have the like leaky ReLU with the same like parameter. And then we are reshaping things to make them go through the conv 2D transpose layer. Then again, the declare ReLU, and then again conv 2D and so on. So at the end, so we have the convolutional layer, okay? So this now is the generator. We're giving it as name, and so later when you see generator, it means that all this code, okay? This is, until now, there is a typical discriminator and a typical generator, okay? And what we will do is now that we are going to create the conditional GAN, okay? So for creating the conditional GAN, we are mainly coding a class, calling it conditional GAN, and it's taking a curious.model. Let's focus on the different methods defined within this class. We have like kind of some initialization here, initialization of the discriminator, of the generator, of the latent dimensions, the what kind of like seed generator you are going to use. Here it's keras.random seed generator. We're giving just this parameter, the metrics that we are going to use. For the generator loss, it's like the mean, and also for the discriminator loss, it's the same thing, the same metric. And then we have these different methods. So we have method metrics, method compile, train step, and so on. Okay, if you want that we go through all these details, I have no problem. Otherwise, you can skip this part because I'm just kind of encouraging you to go through the lab, not more. If you want to do it by yourself, feel free. I'm doing my best to make all the notes and to take a very well commented lab, okay? So let's see. For metrics now, we are just defining the metrics, compiling the method. This is just we are going to use later for setting things like the optimizer, the loss function, and the different parameters to train your GAN. And next, now there is the train step. So we are defining that in details. You can go through that. And let me just make it focus on the training part, which is the most important. So we are calling things defined so far. Okay, so conditional GAN, we are defining it. We are calling this conditional GAN class. We are already like detailing, having a sequential discriminator and sequential generator, and we have as latent dimension an integer. So the discriminator, we are giving it the name. This is the name of the parameter, and this is what we effectively are giving it. So we're giving it a discriminator, generator, and our latent dim. Okay, initializing all that. And next, we're compiling the model, which means that we are giving the settings that are needed for the optimizers. So here we have the discriminator optimizer, and we have the generator optimizer. We have two optimizers. In the other cases, or typical or normal, I would say, typical neural networks, we only have one optimizer, so which is Adam. It's okay, we're using here the same one with the same learning rate, which is 0.0003. But we are using it the same for discriminator and generator. And at the end, we have the loss function. We are using the binary cross entropy. Okay, so I think, okay, I will not train because it will take more time, but mainly this is the output. So because you are supposed to run these cells, okay, but you can trust the output here. Things that what we will do is that we are going to train this for 20 epochs, and If you want to run things, let's run them. Why not? Or it might take some time. Let's see this one. It's supposed to be super quick. This one is super quick. What can take time mainly is the training, but let's do this. No worries. So what will happen is that we are going to train it for 20 epochs. And during the training, what will happen is that we are going to see the discriminator loss and the generator loss. We are using these optimizers, Adam, which is the same for the discriminator and for the generator, in order to minimize the loss, okay? And so it's going to train for 20 minutes, 20 epochs. I'm saying 20 minutes, sorry. So I wish I didn't do this, but it's okay. Okay, let it train. We are going to come back to this point. But when it's training, so it started, the discriminator loss started from 0.4 something. This one started 1.4 something, and then it's going to be like decreasing through the epochs. So we'll come back to this. Next, what will happen is that we are going to interpolate between classes with the train generator, okay? So it gives you the start class, the end class, and you just kind of interpolate between these two classes. And so here is the interesting thing. So the final one after training is supposed to be GIF1, just showing you different images, and it's animated. So I will, you can see this if you are going to go to just wait for the training steps and all, and whenever we will run this. So it at the end is going to like show you how we first sample like noise from a normal distribution, and then we repeat like for the number of interpolations, which is mainly discussed here, okay, defined here, I would say. So this exact number of times we do reshape like the results accordingly, and then we distribute it uniformly for the num interpolation, which is also like defined somewhere. Where is it? Okay, just here it is. In this case, it's 9, okay? We're defining it here, okay? So this is mainly what we are going to use, okay? So we are going so then to distribute it uniformly for that with the labeled identities being present in the same portion, okay? And so it's going to show you how the different like fake images are generated. And so just here's some kind of suggestion how we can improve that using like different, I would say, variants or recipes, okay? So it's mainly giving you the link for this lab. If you want to go through this, can count even like extra points, and or just you can go through it, okay? No need to involve this in the grading. So out of curiosity, if you want to take a look, okay? Otherwise, there is a very interesting resource here I made here with you, which is this book, the Generative Deep Learning one. So Deep Learning with Python, second edition. You can find the chapter Generative Deep Learning, interesting readings if you want, or if you might have time, because even we have a lot of papers to read, many things to do. So all this just remains like optional if you might maybe have the time or you're interested. Otherwise, my focus mainly is to understand the labs, try to play, I would say, with the, like you can, what if, start asking questions. What if instead of training for 20 epochs, I will train for 200 epochs? You can launch this training, do whatever you will do, and come back and compare the results. This is how we learn in Gen AI, and this is how we're supposed to do. This, for example, learning rate is 0.03. What if I will change it? For example, like this, what will happen? So it's all like a space that we don't know if based on this decision, what will give you this result and so on. So you try to change things. You can even play further. You can play with the architecture itself. Like I told you, these puzzles, what if I will add a layer? What I will if I will remove a layer? What happen if like I explore more architectures and so on. So these things I encourage you to do, and this is why I'm going through the lab mainly. It's not to read every single cell, no, to tell you by the end like that you can be the artist and you can be exploring things. You can make some edits. You can modify things, and you can report that. You can like I don't want to give you lots of homeworks, by the way, but I will encourage if you do this by yourself. Yes. So I think mainly that's it for the lab. I don't think we are going to wait for the training 20 epochs because you already have that results. At the end, it's going to converge, and the loss is going to, like I mentioned, we have the value of the loss, which is for the generator in this case, it's decreasing. Okay, for the discriminator here is somehow increasing. Okay, so I think you guys are good, and that's fine. So thank you so much. So these are just examples of generated images. If you have any questions, feel free to ask, and thank you again.